Let's practice using the periodic table to determine electron configuration. Just based on the organization of the periodic table, we can determine the different periods and where the different subshells exist on the periodic table. So each row of the periodic table tells us the energy level. So we have n equals 1, n equals 2, n equals 3, and that continues down. And we know the different areas of the periodic table tell us our subshell. So S, P, D, and F. So let's do an example. Let's figure out the electron configuration for sulfur. So we're going to start from the upper left-hand corner of the periodic table. So we're in energy level 1. So in 1, with hydrogen and helium, we have S2. And then in energy level 2, we have 2S2. And the entire second energy level is full. And so we have 2p6. And now we're getting into our third, which is where sulfur is located. And so we know sulfur is in the p orbital, so we have a full s orbital. And we're in 3p. And we can go ahead and count our electrons. So we have 1, 2, 3, 4, 5, 6 possibilities for the p subshell. And we know sulfur is in the fourth column here, so we have 3p4. And this is our full electron configuration. Now, what if we wanted to do a noble gas configuration? We go back to our most recent noble gas, which is neon. And so we can put neon in brackets. And then we only need to include the following energy level. So here we have neon, 3s2, 3p4. Let's practice writing the electron configuration for a transition metal element. In this case, our example will be chromium, which is highlighted in green on the periodic table. So writing out the electron configuration, we'll start as always with energy level 1, which is 1s2 from the hydrogen and helium. And then we'll move on to energy level 2 with the s block. So for the s block, we have 2s2. And moving to the right side of the periodic table with the p block, we have 2p6. So that is a full shell. Energy level 3 is also a full shell, so we can go ahead and write that in as 3s2, 3p6. And then we'll move to the fourth row of the periodic table, and that's where chromium is located. So this is going to be our last stop here on the periodic table. And we'll start with the S block for S2, and then we know that the D block is lower in energy than the S block, so we'll go back to energy level 3 and put 3D, 1, 2, 3, 4. But this is not where we can stop for this element, and that is due to the rule that we can have no D4s or D9s. And what does this mean? I'm going to draw an example d orbital to show why this is the case. So chromium, we'd have 1, 2, 3, 4 electrons in its outer shell, and this is not energetically stable. It doesn't like having only 4. We want to have all of the suborbitals filled. And so what we're going to do is change our last bit here. And so we're going to take an electron away from 4s2, and we're going to give it to the 3d so that we can fill this last electron in and have it be more energetically stable. So we're going to have 4s1, 3d5. So if we write out this fully, this will be our full electron configuration for chromium, highlighted in yellow. Let's practice writing the electron configuration of titanium. So we know we need to go period by period on the periodic table. So let's start with period 1. And we can write this full electron configuration as 1s2. And then going on to the second period, we have 2s2. We come over to the right side of the periodic table for 2p6. Moving on to the third row, we have 3s2 and 3p6. And here's where it gets a little tricky. We move on to the fourth row of the periodic table. So we know we have 4s2, but because titanium is in the transition metals, we know that the d orbital, we need to do n minus 1. So we have 2 elements in our d orbital. We need to go to 3d2. So that is the full electron configuration. But what about the noble gas configuration? Even though we're ending with 3d2, we still need to use the noble gas that is closest. In this case, it is argon. So in brackets, we can put argon, and that takes care of the third period in the periodic table. Then we can just write 4s2, 3d2. Let's practice writing and drawing electron configurations. Today, our example will be element 11, sodium. So let's start out by writing the full electron configuration. Let's first recall that the left 2 columns of the periodic table represent the S subshell, and the right-hand side of the periodic table, which are typically nonmetals, represent the P subshell. And those are the only 2 subshells that we'll need to know for this electron configuration. So first, sodium. In the first row of the periodic table, we have 1s2. In the second row, we have 2s2 and 2p6. And then sodium is located in the third row of the periodic table, and it's the first atom, so we'll only have 1 electron, 3s1. Now, sometimes you're asked to write the noble gas configuration. And so this means you're condensing the form using the most recent, or like the previous, noble gas. So in our case, that would be neon. So we'd have neon in brackets, and then that gets rid of most of it. I'll underline what we don't need to write now. And then we just have to write 3s1. And that gives us our noble gas configuration for sodium. Now let's draw this out. We have our 1s, 2s, 2p, and 3s. So now let's draw this out. We have 1s2, 2s2. For 2p, we're going to fill each orbital separately and then go back and pair up our electrons. And then we have 3s1. Let's practice writing the electron configuration for an ion. The first step here is to write the electron configuration for the atom, and let's do chlorine. So for chlorine, we're going to start with energy level 1 with 1s2, of course the left side being the S subshell, and the right side of the periodic table giving us our P, and we won't use it for this atom, but the D subshell is the transition metals. So with hydrogen and helium is 1s2, then we've got our second row where we get 2s2, 2p6, and then chlorine is located in energy level 3. We have 3s2, and we've got our 3p, and we've got 1, 2, 3, 4, 5 for chlorine. And now let's write for the ion. So Cl minus means we're adding an electron to get those full pairs for the P subshell. So now our ion is chemically equivalent to the noble gas of argon. So for Cl minus, we have 1s2, 2s2, 2p6, 3s2, and then adding another electron instead of 3p5, we will be 3p6. Let's practice writing the full electron configuration of an ion. Let's start by writing the full electron configuration of the atom of calcium. So we'll start in the first period with 1s2, then we'll go through the second period, and looking at the S block, we'll do 2s2, and then considering the P block, 2p6, then with period 3, 3s2, 3p6, and we're down in the fourth period, and we see that calcium is in the second column, and so as a second group element, we can write it as 4s2. But we're not looking for the electron configuration of calcium, we're looking for calcium 2+. So that is the ion of calcium. So let's go through, and we know we're set at least to the third period, so we can go ahead and write in the same electron configuration up to, let's say, 3s2. And then let's think about where the ion of Ca2+ would be on the periodic table. So we know if we lose one electron, the first column would be +1 for calcium, but we need to lose 2 electrons. So here would be the +2 for calcium. We'd be in the previous, so it would be chemically identical to argon. So that puts us at 3p6. Let's practice writing an electron configuration for a transition metal. I've outlined in purple the element Fe, which is iron, and this will be our example. So for iron, we'll still start with energy level 1 with hydrogen and helium, which are 1s2. Then going into energy level 2, which is the second row of the periodic table, we have 2s2 from the S block. And then going over on the right-hand side of the periodic table, we have the P block. So we have 2p6. Then going to energy level 3, we also have a full shell here. So 3s2, 3p6. And we're going to finish in our fourth energy level, where we have 4s2. And now we're going to go to the D block elements. And because the D block are lower in energy, we're actually going to go back to energy level 3. So we have 3D, and we have 1, 2, 3, 4, 5, 6. And that is the electron configuration for iron.